Chen, who's going to be talking about some research conducted over Singapore.
Thank you very much, Matt, for the nice introduction. And hello, everybody. My name is Song Chen from Center for Climate Research Singapore. I would like to start with thanking my collaborators list over there. So without their contribution, this work cannot be presented here today. So I would like to start with some background. So Singapore, as you know, is a highly urbanized tropical coastal city and very hot all year long. And there's also a few very interesting weather systems in Singapore. Yeah, different type of rains. And one of them is called localized thunderstorms. It appears during a certain month. We call it intermonsoon seasons. Both the time scale and the spatial scale is actually very small. It can be like 1 or 2 kilometers or even smaller than that. So the time can be like 1 hour or even half an hour. And so that's why for a city state like Singapore, we want to go to high resolution, try to get those information right in our model. And from the climate wise, yeah, we are also very kind of worried about the future urban heat climate in Singapore. We care a lot about the heat. And of course, air quality in a city state fully packed with almost more than 6 million people. Yeah, can be an issue as well. So with all of these things considered in mind, we would like to tackle those problems using our model called uSINGV here. So U actually represents urban. And this model is developed based on the MetOffice unified model. And the urban part is handled by MetOffice. It's a single layer urban canopy models. So currently we run the model from the operational 1.5 kilometers SINGV model for the weather forecasting in Singapore down to 300 meters and down to even 100 meters. So you can see the scales, the domain size marked on the plots on the right over there. And so far we started this project last year. So far we have managed to come up with the latest surface representation. So this is the land use land cover over there. We use 9 tiles, and the urban is further split into roof and the canyon. Use the latest data for Singapore. And after the Singapore, we also managed to find some open data, try to as realistic as possible. So that's what you see over there right now. And we also got a little bit of preliminary results so far. So that's one of the preliminary results. Vertical velocity in the middle of the boundary layers. So you see those kind of streaks, also a lot of overturnings, and quite a turbulence-like. And actually, we also did this TKE spectral analysis over there, kind of confirmed during the convection boundary layers, our current model at 100 meters kind of start to resolve scales up to probably 600 or 700 meters. That is within the inertial subrange over there, follow the slope -5 over the 3 over there. Before going to a little bit more results about the boundary layers, and of course we have to compare model data with observation as much as we can. So here you see that we compare the model with flux towers. So there's net all wave radiations, and there's also sensible heat and the latent heat flux over there. And it kind of a little bit messy, many lines over there. But if you look at this black line, it's actually observation, and there's a D3 marked over there. It's the results from 300 meters model, and the D1 it's from the 100 meter model. And there's some other like D1 with R is regraded the very high 100 meters to the 300 to do the comparison. And there's additional one, D1 adjust, with some kind of a wind direction adjustment made to check whether the sensitivity the model provides. But from those results, you can see that so the all wave they are matched with the observation quite well. Although you can see that kind of sensitive when we do those regrade, when we do the adjustment, you can see the changes from the sensible and from the latent heat flux over there. And we also compare with other type of the observations. So stations, here you see the 1.5 meters air temperature. On the right, it's the contours, so 300 meters and then 100 meters. Actually, if you look closer, there's much more details from the 100 meters over there. That is kind of what we expected. We hope to use high resolution to get a little bit more details from the model. And on the right, it is the diurnal cycle. Again, you will see the black line observation. And from the 300 meters and the 100 meters, the shaded areas is standard deviations from the model results. They actually match the diurnal cycle very well. And we also see kind of Sorry, let me bring pointer. Oh, somehow not bringing up. But anyway, so in the nighttime, we also see kind of an improvement from the very high resolution, 100 meters. Similarly, we also compare 10 meters wind speed. And again, you will see those detailed structures from 100 meters and the diurnal cycles also matched with observation relatively well. And then we come to take a look at those, what is happening in the models for the pendulates part. So here I'm showing you two cut planes of a vertical winds within from the ground up to like 2 kilometers. And the first row it's 1.5 kilometers resolution, and then from the top to bottom go to high resolution 100. So very clearly you can see a lot of the happenings from the high resolution over there. We start to see those red and blue components over there. Actually, they represent those updrafts and the downdrafts. Just to give you another view, the three-dimensional features of those structures. The white part actually is what you see, those updrafts rising from the ground. And you also see some blue structures. They are the substance representing the air come towards the ground. So if you follow the timestamp over there, they are kind of actually showing up during the noontime and generate a lot of them and start to disappear after the sunset. And we also checked those cloud liquid water at this two cut planes. And again, we found this interesting phenomenon over there. A lot of clouds seem to show in the high resolutions. But we want to, similarly, we want to see what they look like in the three-dimensional. This is another animation. So you see clouds coming from that direction, following the magenta arrows showing the wind speed at that height, and the black arrows is really the wind speed near the ground. So those clouds coming from that direction start to pop up. So we were wondering whether those clouds are kind of real or not. We are very fortunate to, at this specific day, we find this satellite image from Sentinel-2A, and not at exactly the same time, but you can see, you can compare the model cloud representation with the satellite image. Not exactly the same, for sure. A lot of difference if you compare the clouds, but you can start to see some kind of like a street clouds following that direction, following that angle, seems to match with the observation. So that's give us a little bit like a motivation. It seems we are going to the right direction. Another question we have been asking ourselves is that, so whether the vertical resolution is important or not. So all of the results I'm showing so far, we are using 80 vertical levels. So from the bottom surface all the way up to 38.5 kilometers. And so in these cases, we also try test whether we should include more vertical points when we include the horizontal resolution. So here, the new vertical coordinates is 154, we add more points from the bundulars all the way up to the troposphere over there, and you can see the point distribution on the right. And if you zoom in, actually follow the green line over there, that's the distribution for the new one. Yes, it's a lot of things actually happened here. Model stability issues, it's not so simple as it seems to implement the new vertical coordinates in our model, but we managed to get it wrong. And again, we try to compare with the observation to see what is going on if we introduce these changes. So we compared the model data with radio sound. So the first plot showing there is the potential temperature. And there's actually a lot of lines over there. So with red, green, blue, they are the previous data with 80 levels. And the black line is the 100 meters using a new vertical resolutions. So you do not see much difference from potential temperature, but you start to see difference from specific humidity and see more difference from the horizontal wind. But actually, if you look a little bit closer near the surface, this new vertical resolutions seems to be able to provide a little bit better agreement compared to others, but difference is quite obvious in the upper air regions. Yeah, I need to point it out. So for this comparisons, it's kind of a simple comparison. The model data is a fixed location, kind of like a snapshot. But when you compare to with radio sound, the balloon is actually can be drifted away. For these cases, it was drifted away more than 60 kilometers. And it's of course, it's not a snapshot like a model would have. So those are things we have to consider if we want to do an even better comparison in the future. So yeah, here's the short summary. I got a chance to show you the development of 100 meters uSINGV and compare it with many observations as much as we can. And we see some very interesting phenomena so far, for example, from the turbulence from the clouds. And we also did some testing with the vertical resolution, but still a lot of work needs to be done to understand those issues better. And all of the information so far is no rain days to make things simple. Next step, we are also going to try it to those to test the model for those high impact weather in Singapore, which is extreme rainfall, extreme wind, for example. So I will stop here. Thank you very much for your attention.
Questions from the audience? Thank you for bringing us back on schedule, Dr. Chen. Where's
So if you're changing the vertical resolution, do you do anything to the bending line?
We haven't touched it yet. Yeah.
So it seems like you have some roll vortices from the observation, but maybe you're modeling. Have you analyzed your outputs with the up and down graphs to see if you have this kind of scale that is like the roll vortices that's observed?
Sorry, do you mean the observation to show those updrafts, downdrafts, and rolls?
Right. You had clouds there that showed like roll vortices.
Yeah, yeah. The only observation we get so far is this satellite image. So yeah, if there's observation available, yeah, it would be very nice to confirm whether those street clouds really within. Yeah, thank you.
Amazing.
All right, please join me once again in thanking our speakers. And up next